Okay, right, we're going to talk about at the fairground today, and we're going to apply some of our circular motion techniques that we have to situations at the fairground. So we're going to imagine we're off to Thorpe Park and we have managed to get there. Okay, so we're going to look at 3 different situations where circular motion can come into sort of planning for a fairground. So our first situation, we're going to have a look at the Big Dipper. So basically a roller coaster. And we're going to imagine, first of all, that we are looking at the roller coaster car on its own, and there's a person in it. So here's the person sat down. Excuse my terrible drawings. Let's consider the forces for a second. So that person has got a weight, and that weight is going to act downwards. So we've got mg. But if we only had the weight, that person would be accelerating downwards at a rate of g. So it's not going to be quite just that. Instead, we have got a opposing force, which would be the force of the roller coaster on the person, which we can call a support force. Now, there's a reason why I've looked at this situation with just a very basic roller coaster on its own before we've looked at a situation with circular motion, and that's because this is going to help us with our understanding. So let's now think. Here is the bottom of my Big Dipper. We've come down, so some support struts in here. We've come down from a hill, and the roller coaster car is there at the bottom, and it's going through a bit of a parabola. It's going through this kind of circular motion, and hence we're talking about circular motion here. So that roller coaster car will have a forward velocity, which we'll call v. It will also have the weight, and we're going to consider the person in here really for the moment, the weight of the person, which we're going to call mg. It could be the weight of the car if we want it to be, but we'll go with just the person for the second. And it will also have a support force that is acting upwards towards the center of this invisible circle as this car moves round. So it's coming down here, and every time it's in this kind of invisible circular motion relative to that central point here, it's moving in circular motion itself. So when we had no circular motion, when we had the car on its own, we could say that the support force was equal to the weight, because no one's accelerating anywhere, and we're dealing with Newton's first and second laws here, really. But when we're looking at this situation, we've now got that centripetal force acting towards the center of the circle, because we have to have a force that's pulling that car inwards as it's moving through the curve. And that force is going to be the support force. So the support force is going to be bigger than the weight, because it has the centripetal force pulling upwards to make that car move through that circular motion. So we can define this as support, because that's the bigger one, minus weight is equal to my centripetal force. Well, my support force we've seen so far is S. My weight is mg. And what we haven't talked about is the centripetal force. Well, the centripetal force is still the same as we've looked at before. So mv squared over r. So we've got S minus mg, so support minus the weight. So what's left of that force is acting upwards towards the centre, which is going to be our centripetal force, which is mv squared over r. So the extra force, and we can work this out because we can say, well, support force, we'll go with S, support force is equal to my mg so my weight, which is where we were when we weren't moving, back over here, plus this force due to the centripetal force. And that extra bit there is our extra centripetal force, which is pulling us inwards. Okay, so this is one of our equations. And this centripetal force tells us how much support force we need at the bottom of this roller coaster ride. So we could work out what the strength has got to be of this roller coaster here, because it's got to be greater than at any other point because it's pushing upwards and it's got to keep that roller coaster moving upwards. So that's our first situation, and we'll come back to that situation in a moment. We'll come back to it with a question in a moment. So we're going to go on to the second one now, which is a long swing. So, situation 2. It's kind of like a pirate ship. That's the way I like to describe this one, really. So, situation 2 is the very long swing. I don't know how long it has to be very long. But anyway, a very long swing. I think we'll consider it as a pirate ship. So, when we have the pirate ship at Thorpe Park moving, it's not going to be a great pirate ship, sorry, moving downwards, so it's going to start there, it's going to track through this curve and then track back up the other side, because obviously that's what pirate ships do, then we're going to have, again, a point at the bottom where it's going to have a bit more force. Now, the difference between this and the roller coaster is that actually the pirate ship, I don't like that where that is, let's go there. The pirate ship is going to be attached by a single length of rope, we'll call it rope, I know it's not rope, it'd be metal, but a single length of material which is going to have its support force. So we pulled this pirate ship up, and let's go relative to a central point. So the same central point here. We pulled it up by a distance h. So it has gained potential energy here. So if we consider, let's draw ourselves, well, 2 colours, and we'll draw ourselves some energy stores. So potential energy, which we'll call red, is going to be at the maximum, right at the top here, and kinetic energy, which we'll call blue, is going to be right at nothing. But once it swings to the bottom here, this is the lowest it can go, the potential energy is going to become nothing, but the kinetic energy is going to go to the maximum. And in theory, if we're not losing any energy, then those two maximums should be the same. So that allows us to start calculating something about it. So we'll use kinetic energy, half mv squared is equal to gravitational potential energy, mgh. So we're using ek is equal to ep. Well, first of all, hopefully you can spot that we can cancel those two m's. So we can say a half v squared is equal to gh, which means we can say that v squared is equal to 2 gh. So the square of my velocity at this point here, and I haven't put a velocity on, so let's have a velocity. What colour haven't I used? Green. So we'll have a velocity here. The square of that velocity at the bottom is going to be equal to 2 times the gravitational field strength of the planet we're on, if it's Earth, 9.81, multiplied by the height we've moved it through from this point here up to this point here. Okay, well, hopefully you can see we're going to use that v squared in a moment. So let's consider the forces on that on this pirate ship at the bottom. We have still got a support force that acts towards the middle. And we have still got a weight that's acting downwards. So in fact, we're pretty much the same as the previous equation. We've got the support force minus the weight, and it has to be that way round because the support force is pulling the pirate ship in. If we didn't have more of the support force, this pirate ship would go off at a tangent in a straight line. If we didn't have it attached there, it would just drop straight down. If we didn't have it attached at this point here, it would just go in a straight line there. If we didn't have it attached at the bottom and it still had that velocity, it would go in a straight line in that way. So it's that support force that's changing the direction of our velocity, which is causing us to have the acceleration, and that gives us our centripetal force. So S minus mg will give us mv squared. Now, not over r, because we know what r is. We know that r is, in fact, h. So, mv squared over h. In the book, it might be L, but it makes no difference what letter we use. But we can use the v squared we've got from this equation, our energetics equation, in our centripetal force equation. This is the beauty of physics. So we can take this v squared here and plop it into here. So we have S minus mg. It's going to give me 2 gh m. So 2 mgh over h. Give me a second, hang on. Not so happy with h because h is not quite the same length. So this would be length L. I take it back, that would not be h, that would be L, and that will be L. Sorry. So that will be L, and that will be L. So we're going to change it because L is the distance from the point of rotation to, well, the length of that radius effectively. So our extra support force then, so talking about where we've got it from, so that extra support force is going to be 2 mgh divided by L. And that is what's going to give us our centripetal force and allow that pirate ship to move through those directions. So that's the very long swing, and actually I've got a little proof here that we're going to do, and it's not a proof you have to learn, it's just a proof as in mathematical, can we prove something? So prove that when h is equal to L, so that's a 90-degree swing, the extra support force is equal to twice the weight. So we could see this in a real exam question. So where do we start? Well, let's take the equation we know. S minus mg is equal to 2 mgh over L. So we can say that the change, or the extra bit of force, is going to be our 2 mgh over L. And if h is equal to L, then we've got 2 mgl over L. Cancel the two L's and we're left with 2 mg, which is twice the weight. So we proved it because that means that that extra force is equal to twice the weight. That kind of gives you an idea as to why they don't move those pirate ships to 90 degrees. If those pirate ships get to 90 degrees, the double the weight is what you have to have of the support force to hold the pirate ship in. If you move it to less than that, obviously you're going to have a lower force. So it's quite important to kind of have an understanding of this if you were ever to be building roller coasters or theme parks. Okay, so let's go for the third example here. Now I'm going to use the example of a big wheel, but it can also be for a loop-the-loop of a roller coaster, and we might talk a little bit about that before the end of this video. So the big wheel, and Let's draw ourselves a big wheel. So we might have something at the center that's holding it up, some support struts, and then we've got an object at the top. So we're considering this point at maximum height. So that capsule is moving, has a velocity, it's moving around the big wheel itself. So the force, let's put some radial spokes on here, the force that's stopping that capsule from flying off is in fact a downward force, because the next step is that capsule is going to be over here and our velocity is going to be in that direction. So it is an inward force that is holding that capsule onto that circular motion. So the force stopping the capsule flying off is what we're going to call R, the reactionary force. Okay, so it's a force pushing back down. So if we now consider that capsule right at the top, so here's the capsule right at the top, we have two forces effectively acting downwards. We have the weight of the capsule, but we also have this reactionary force R. So that means we can say mg plus R is going to be equal to our centripetal force, mv squared over R. So we can also say that R is going to be equal to mv squared over R minus mg. So let's look at an example of kind of the limits of this equation. So we'll just get rid of that bit there. So if v0 squared was equal to g times by the radius, what would we find happen? Well, let's have a look. So we've got R is equal to mv squared over R minus mg. We're saying that v squared is gr, so that means I've got m lots of gr over R minus mg. Well, R divided by R is 1, so I've got mg minus mg, so that's 0 newtons. So when our velocity squared is equal to gravity times by the radius, then we've got no reactionary force. So effectively, this is where you would feel the weightlessness going round a loop the loop. So let's do a question. Let's use this now and make sense of how we can put this into sort of physics concepts. So we've got a loop the loop here. They're not often circular, but that's sort of slightly different reasoning. So we've got our carriage at the top. It's got a forward velocity, v. We're going to say it is circular and it has a radius of 10 meters. And the force acting downwards is going to be mg plus R. So we want to work out, calculate the minimum speed for the roller coaster to remain on the track when at the top when R is equal to 10 meters. So what's the minimum speed for that to happen? So for it to remain on the track, we need to have that the V0 squared that we looked at previously has got to be equal to G times R. So in this case, G is going to be 9.81, effectively 10, multiplied by 10. So that's going to be roughly 100. I'm going to do this as a back of an envelope calculation. So V0 then would be the square root of that, which is going to be 10. So the minimum speed, roughly 10, is going to be roughly 10 meters per second to go around that loop-the-loop. Any slower and it won't remain in contact at the top. So you'd have to have some kind of support force acting upwards to hold it on. Any faster, and obviously you've got a greater centripetal force towards the center. So that's the minimum speed at which you can go round that loop-the-loop without losing contact with the top. Okay, right. I've got some exam questions, or an exam question that I would like to go through with you. So let me just get the right one. Let's turn you on, turn you off. There we go. Right, so we're going to have a look at question 3 here. Now, this one always trips people up, and this is from physicsandmathstutor.com. So, and I will attach this to the files as well, so you can see it in your own time. But we're going to have a look at it together. So it says, Figure 1 shows a fairground ride called a rotor. Riders stand on a wooden floor and lean against a cylindrical wall. The fairground ride is then rotated, and when the ride is rotating sufficiently quickly, the wooden floor is lowered. The riders remain pinned to the wall by the effects of the motion. When the speed of the rotation is reduced, the riders slide down the wall and land on the floor. At the instant shown in Figure 2, the ride is rotating quickly enough to hold a rider at a constant height when the floor has been lowered. Okay, so we've got picture Figure 2 below. Draw onto Figure 2 arrows representing all of the forces on the rider when held in this position relative to the wall. Label the arrows clearly to identify all of the forces. So, quite important to be able to do this because there's always going to be questions where we need to draw forces on. And so we've got the wall, we've got the person, so there's the person sort of leaning against the wall. It's not a very good indication, but anyway. So three forces that we can draw on. The first is going to be this person's weight, which is going to act downwards. Now, if the weight's acting downwards, this person should slide down. So that means we know that there is another force acting upwards. And that force is going to be between the two objects that are moving. And because those objects are moving, so it needs to be between the wall and the person, this is a friction force. So we've got a weight acting downwards, we've got a friction force acting upwards. And so what other force have we got? Well, we have got our centripetal force acting towards the center. So the weight is going to act from the body downwards. The frictional force is going to act upwards, stopping the body from sliding down. The centripetal force is going to act inwards, holding the body on that wall as it rotates round. Because remember that this wall is part of the rotor, which sort of looks like that. So he's sat on it, and as it's going round, he's being held to the wall. So it's that centripetal force which is making him move round. And in fact, it's a support force of the wall on the person. Okay, so that's our first question. Let's move on to the next one. So it says, explain why the rider slides down the wall as the ride slows down. So, why does the rider slide down the wall as the ride slows down? Well, it must mean that the frictional force is smaller, because that's the only way you can end up sliding down. The frictional force must be smaller than the weight, and that's the first point I would write down. Hang on one second. Let's get the answers up to make sure we're talking the right ones. So the friction gets smaller because you are not being pushed in as much. So got to think very carefully about what it is they're going to want to see here. So it says, why does the rider slide down the wall as the ride slows down? That's because if the ride slows down, we know the centripetal force is mv squared over r. So if v gets smaller, then centripetal force will be smaller. So that means you're not being pressed in as much into the wall. So if the centripetal force gets smaller, that reactionary force, that force that's pushing outwards, is also smaller. So reactionary force is smaller. So centripetal force is smaller, reactionary force is smaller, and that means that the frictional force is smaller. Be smaller than the weight. Which means that the person then is going to accelerate downwards because the difference in those forces means that there is a resultant force, change in force acting downwards, so that person will slide down. Okay, right, so wordy question done. Let's go on to our calculation question now. So it says, at the maximum speed, the centripetal acceleration is 29 meters per second. Show the maximum angular velocity of the rider is 3.6 radians per second. So it's always quite nice to have a show one because that makes life quite easy. So we're going to use the information we've got. We know that the acceleration is going to be 29 meters per second, and we want to show omega is equal to 3.6 radians per second. That's the aim of this calculation. We also know that acceleration is equal to v squared over r. So v squared over r is equal to 29. We're told the radius, we're told the diameter. Now let's be very careful here. It's where I went wrong when I practiced this. The diameter is 4.5 meters. So the radius must be half of that, 2.25 meters. So be very careful before you go any step further than that. So 29 is going to be equal to v squared over 2.25. So v squared then is equal to 29 times by 2.25. All square rooted. We'll do that as a multiple step. So we've got 29 times by 2.25 and then square root of that answer, which gives us 8.077 meters per second. So that's its linear velocity. And we want to work out the angular velocity. So omega is equal to, is going to be v over r, which we obviously know. So that'll be 8.077 divided by the radius 2.25, which is going to give me an answer of 3.59 radians per second. So have we proved it? Did we prove it's 3.6? Yeah, because it's going to round up to 3.6, especially when you consider that everything in the question is 2 sig figs. So we go to 2 sig figs, that becomes 3.6. So we've worked that one out. We don't need to do the next question. This one about torque is not on the spec for us. It seems to be in the documentation here, but it's not on the spec, so we'll move on. So it says, calculate the centripetal force now of a rider of mass 75 kilograms when the ride is moving at its maximum angular velocity. So we get rid of this. So we now know the rider's mass. So his mass is 75 kilograms. We know we're working at the maximum velocity, which is going to be 8.077, which we worked out from a previous question, carrying it through. And that's all we need. So, we need to know R. R is 2.25 meters. So we know that the centripetal force is going to be mv squared over r. So it's going to be 75 multiplied by this 8.077 squared divided by the radius 2.25. Put it all in your calculator. It's be 75 multiplied by 8.077 squared. Divide that by 2.25 will give us an answer of 2,174 newtons, approximately equal to 2,200, especially if we look at sig figs again, because it's 2 sig figs for each one. So nice and straightforward. Again, only 1 mark for that one, so you're not going to get many marks at the end for that. So we'll do the last part now. Figure 3 shows the final section of a roller coaster, which ends in a vertical loop. The roller coaster is designed to give occupants a maximum acceleration of 3g. Cars on the roller coaster descend to the start of the loop and then travel around it as shown. So now we can see the picture. The cars coming down the hill. We've got 3 points C, A and B, and the direction of travel is anti-clockwise as we go round. So at which one of the positions marked A, B and C on figure 3 would the passengers experience the maximum reaction force exerted by their seat? Circle your answer below. So we've got to think, where is it going to have the maximum reaction force? Remember that maximum reaction force really is going to be our maximum centripetal force. So if we go back to our centripetal force equation, for this to be maximum, M can't change, R can't change, only V can change. So at what point is it going to have the highest velocity? Well, it's in fact going to have the highest velocity at point C. So the answer to that one would be point C. Here it's got the highest velocity because it had maximum potential energy here, picking up maximum kinetic energy here, going to a much lower kinetic energy up here, and then coming back down again. Okay, so C is the right answer for that one. And explain why the maximum acceleration is experienced at the position you have chosen. This will be the last bit of this session. So we need to explain why. Well, because centripetal force is mv squared over r. The maximum velocity is reached at the bottom of the hill. As all PE changed to KE. We also know that R is equal to MA plus MG, where A is the V squared over R from up here. So R is maximum at this point. And it's maximum because remember that A is equal to V squared over R, and A becomes maximum when V becomes maximum. So that's our 2 marks there. So 14 marks, although we'd have lost a couple because we wouldn't have done the talk one. So 11 marks there. So it's 11 marks on this topic entirely. So you can start to see how they start to bring all of these parts together. Okay, so this is the end of the circular motion topic. So further mechanics, we've done our first topic in A level now, and we're going to move on to applying this into SHM in the next video.